Are you able to see the screen?
Yes, sir.
Okay. So I welcome you to the week 7 of the live sessions for the course Basics of Finite Element Analysis Part 2. So the course instructor, as you might already know, is Professor Dr. Nachiketa Tiwari from IIT Kanpur. Introducing myself, I am Vikram Balaji, a research scholar from the Department of Mechanical Engineering at IIT Madras. So you might know in total we have 8 live sessions corresponding to 8 weeks of the lecture. So this is week 7 of the live session, which means there is one more live session which will be the last live session next Monday. So this is the week 7. So let us go into the session. So these were the contents of the week 7 lecture of the series. So if you see, so there are four main topics which were covered in the week 7. So the first topic was evaluation of boundary integrals. So if you have an element, how to evaluate two-dimensional element, how to evaluate the integral along the boundary. So that is is required for evaluating the boundary terms. So secondly, we have assembly of 2D finite elements. So once you have the individual stiffness metrics for each and every element, which we saw in the last session also, how to get for linear triangular element, and one we saw for a bilinear rectangular element also. So for those two type of elements, how to assemble the different individual stiffness matrix to get the global stiffness matrix. So the third topic is we also saw an example problem of the two-dimensional FEA with one variable, so which is the heat transfer application in a two-dimensional plate. So the last topic was numerical integration scheme for two-dimensional problems. So this involves mapping the element from the physical coordinate system to the natural coordinate system and evaluating the Jacobian of the mapping or the transformation. So with this in mind, we will see some sample assignment questions which will be both in the subjective as well as in the objective fashion. So that will cover the week 7 lecture contents. Okay, so we shall now go into the session. So if you have any doubt, please you can ask in the middle also. So as we discuss the questions, so as and when you get doubt, you can please ask the question. I will try to answer. Okay. We have
Okay.
yes. So this is the first question. So we have three cases. So in each case we have a linear triangular element. So triangular element in the sense we have three nodes and three sides, and we have three cases of application of the boundary. So boundary source. So what we have to do is evaluate the boundary source integrals for the following three cases of Qn is given, and elements which are shown below. So on element sides where Qn is not shown, assume that it is 0. So for example, in this element you can see that it is the boundary source is there for side 1, 2. So for the other two sides it is not shown, which means we can assume it as 0. So there are three cases totally. So we will solve each case one by one. So for this I will take the help of these notes. So I will go here. So first of all I will try to draw this element. So I number this node as 1, this node as 2, this node as 3. So the case is we have a uniform application of boundary source which is equal to Q0, which is a constant. So I will try to draw this here. So Qn of S is equal to Q0. So S is nothing but this coordinate system. So let us say I am representing a coordinate system with 1, 2 as my x axis. So rather I would say the s axis, and the perpendicular is the t axis. So first of all we need to know the formulation for that. So let me assume that this is my general xy coordinate, in which I have the coordinates of 1 as x1 comma y1, uh, x2 comma y2 for the second coordinate and x3 comma y3 for the third coordinate. So from this coordinate system, first of all, to evaluate the boundary integral along the entire boundary, so 1 2 3, so it's a triangular boundary, so along the boundary we need to evaluate the boundary term. So let us try to recall what is the FEA equation. So in short, I will say that in a global manner, I can say my, or I can say in a element. So since we are dealing only with one element, I can say it's for single element. So K, the stiffness matrix into the displacement will be equal to my force term, and there is a boundary term. So this is what we are interested in this question. So this is the boundary term. So how will you represent the boundary term? Means, so let us say we are having Qi. So here I ranges from 1 to 3. Since we have 3 nodes, so we have 3 equations in total. So what is Qi? So Qi is nothing but my boundary integral along the element. Rather, I will represent this as capital letters. So I'll write capital Qi is equal to Qn into psi I into ds. So what is ds? ds is a small line element along the boundary. So for this it will be this will be the ds. And what is Q1? So if you have seen in the previous live session, or if you recall from the lectures also, we know that Q1 is nothing but this term, which is you can say so Q1 was, you will, if you recall from the lectures, it will be nothing but dou u by dou n, which is nothing but directional derivative. So here the Q1 is already given for us, so it doesn't matter. So when we will see in the further examples, we will know how to evolve Qn. Or if you recall from the model equation, weak form, so you would have one terms for Kij, you will have terms for F, and you will have terms for Q. So Q, if you recall, it will be in this fashion. So I will say rather my Q will be, I will go a little down. Integral along the element. So W, this will be my weight function into F1 nx plus F2 ny ds. So what is W? W was the weight function. So this I hope you understand, because this we have already seen in the last lectures also. So are you aware of this term, this Q boundary source? So what is F1?
No, sir,
Okay, you are not aware, huh? Yeah. So actually it's nothing. So we
no,
okay, so this is a general equation for finite element. So how to derive K, how to derive F, how to derive Q. So these are all there in the previous lectures, and this is the term for Q actually. So Q is nothing but the W is a weight function, and F1 nx plus F2 ny. So what is F1 F2? We'll just see. F1 is nothing but my A11 dou u by dou x plus A12 dou u by dou y plus this will be my F1, okay. And what will be my F2? A21 dou u by dou x plus A22 dou u by dou y. So this you might are you familiar, this F1 and F2? So this f1 f2 actually we got from the model equation. So if you look back in the previous lectures, so we have a general equation, differential equation of this form. So let me write that also to avoid confusion. So generally the differential equation is model equation. So minus dou by dou x of a11 dou u by dou x plus a12 dou u by dou y minus dou by dou y of a21 dou u by dou x plus a22 dou u by dou y, and we have plus a00 into u minus f is equal to 0. So this differential equation you might have seen, right, in the previous lectures. This is called as the model equation. Okay, so this model equation only we have applying the weak form, and we are getting some terms. What is the this is the elemental stiffness matrix, this is the force term, and this is the boundary term. So boundary term is nothing but, we already derived in the last class, it is nothing but your weight function into product of f1 nx plus f2 ny. So f1 is nothing but this term. So this was f1, and this whole term is f2. So you just multiply by w and take the weighted residual integral, and we get the weak form, and finally if you apply you will get this q term. So this I am just reminding you what is q, because we may use this in the subsequent questions, but for this case the q is already given, so we do not have to worry. So for just explaining the terms I am telling these things. So I hope there is this thing clarity. So we will just proceed now. So how to evaluate the boundary integral for this case? So as I told, first of all we are in the xy coordinate system, and we need to shift to the st coordinate system, because I have to do integral along the boundary, and I have only the boundary system only at this particular edge, and the other two edges there is 0. So I just shift my coordinate system to st, so that I can simply integrate as a single variable. So along the s I will be able to integrate. So first of all we will do the transfer of coordinate system. So for that I am going to write in this manner. So I will write x as summation of p1 plus q1 into s plus r1 into t. Similarly y I will write it as p2 plus q2s plus r2t. So essentially I am writing x is some linear function of s and t, and similarly y is also a linear function of s and t. So this is how I represent. So I'll write a small table over here. This will be my node, this will be my coordinates in the xy coordinate system, this will be my coordinates in the st coordinate system. So I will go back to the drawing over here. So this, let us say, is h12, which is nothing but the distance between 1 and 2, and let me put the perpendicular height of this as let us say, or I'll make it more generous. I'll put this as a, I'll put this as b, and this distance I will call as c. So if you see in this coordinate system, so I'll write the coordinates here. My 1 will be 0 0, because my coordinate system starts at this point, and here I will get the coordinate for point 2 as a comma 0, and for this point I will get coordinate as, this is along c, along this direction c, and along this direction of b. So I will get c comma b. So I hope there is no doubt. So is there any doubt in this new coordinate system? So the coordinates, so how I got that one? I just place the coordinate system along this side 1 2, I just this side 1 2 I made it equal to a, and the height I assumed it as b, and the distance of the third coordinate system from the point from this t axis is c. So my coordinates will be 0 comma 0, a comma 0, and c comma b. So we'll go to this table. So my node 1 was x1 comma y1. So this was 0 comma 0. So this is x2 comma y2. This was a comma 0. This is x3 comma y3. The coordinate system is 0 comma b. So these are the three coordinate systems, three coordinates of the point in the ST coordinate system. So I will just substitute these things. So if I substitute the value of node 1, my x will become x1. The s and t I will just substitute 0. What remains is my x1 will become p1. So this is one equation. Similarly, my y1 will be equal to, it will be p2. Correct, because my s and t are 0. So I get these two equations from node 1. From node 2, what is x2? p1 plus q1 times of a plus r1 times of 0. So this I so last point I substituted this. Now I am going to substitute this. So q1 times a plus r1 times 0. So my x2 will be p1 plus a times of q1. So my q1 will be x2 minus p1 by a. So p1 was nothing but x1. So I write it as x2 minus x1 by a. So similarly for y2, if I substitute, y2 is equal to p2 plus q2 times of a plus r2 times of 0. So similarly I will get q2 is also equal to y2 minus y1 by a. So it's very similar to this, because my p2, if I substitute as equal to y1, I will get y2 minus y1 by a. So so I got two more terms. So I have now another two more terms. So from this we have got what is p1 and p2 we have got, and q1 and q2 we have got. The next remaining is r1 and r2. So for that we have to substitute the value of the node 3 coordinates. So from node 3, my x3 is equal to p1 plus q1 times of c. This is not 0 comma b, this will be c comma b. I am substituting this point, plus r1 times of b. So what is my r1 from here? So I will bring all the terms this side, x3 minus p1 minus c times q1 is equal to r1 times of b. So what is r1? x3 minus p1 minus c q1 by b. So I can substitute the terms. If my p1 is nothing but x1, my q1 is nothing but x2 minus x1 by a. So this whole total divided by b. So finally what is r1? So if you see the x1 coefficients, here there is a minus 1, here there is a plus c by a. So I can say c by a minus 1 into x1. Then you can say minus c by a times of x2. Then plus there is a single of x3, the whole divided by b. So this was my r1. So same thing I will do for y3 also. y3 is equal to p2 plus q2 times of c plus r2 times of b. So from this again r2 I get the value as y3 minus p2 minus c q2 by b. So p2 was nothing but y1 minus c times of q2, again we have to substitute this one, y2 minus y1 by a. So same similar, very similar equation you will get. R2 is nothing but c by a minus 1 into y1 minus c by a times of y2 plus y3 by b. So from this equation we have got p1 q1, p2 q2, r1 and r2 also we have got. So finally we substitute everything here and get x and y as a function of s and t. So why I am doing all this? So I am doing this because I want to convert the coordinate system from the normal xy coordinate system to the st coordinate system. So my st coordinate system, under st coordinate system it will be very easy for me to evaluate the boundary integral along this line. Okay, so that is why I am doing all this. So what is my x? So substitute p1 is going to be x1 plus x2 minus x1 by a into s plus this whole thing c by a minus 1 x1 minus c by a x2 plus x3 into t by b. So again I will bring this a in the denominator of here. So by a I will make it. So like this I will make it. So this is nothing but you can see x is a function of s and t with constants being the x1, x2, x3 those stuff. Y very similar equation y1 plus y2 minus y1 into s by a plus c by a minus 1 into y1 minus c by a y2 plus y3 into t by b. Okay. Okay, so we have solved for x and y. So I will just ask a question. Along the line 1 2, what will be the value of t? Can anybody tell? In the st coordinate system. So this is my line 1 2. Let me highlight this. So what will be the value of t?
0.
Yes, 0, correct. So I will substitute. So for this I will say along line 1 2 I will substitute t is equal to 0, correct. So what will be the x value? X will be simply x1 plus x2 minus x1 into s by a, because this entire thing, if I substitute t is equal to 0, this entire term is going to vanish. This will simply vanish in both the cases. So I can simply write this. I will group the x1 terms together. 1 minus s by a times of x1 plus s by a into x2. So this I can call it my psi 1. Sorry, not psi 1. Let me keep it as it is. Let this be as it is, and y will be equal to y1 plus y2 minus y1 into s by a. So again this will be 1 minus s by a times of y1 plus s by a times of y2. Okay, so we have got x and y in terms of s and s alone. So here there is only s there. So what we are going to do, again we have to recall one thing. So what was the shape, not shape function, interpolation function. Interpolation function for a linear triangular element. So I will just write the equation interpolation function. My psi I is going to be 1 by 2a times alpha I plus beta I x plus gamma I y. So does any of you remember this equation? You have seen this equation in the last lecture also. So what will be my alpha? So alpha I, any guesses? Do you remember? So what was alpha, what was beta, and what was gamma? and A is nothing but the area of the triangle. Right? So if you don't remember, I will just write here. So alpha is nothing but xj yk minus xk yj. Does anybody remember this? So we have, let us say, ijk like this. So it is in a cyclic fashion. So if my I is equal to 1, my j will become 2 and k equal to 3. So what will be my alpha 1? It will be simply x2 y3 minus x3 y2. Similarly, alpha 2 will be x3 y1 minus x1 y3. So when I becomes 2, j becomes 3, this becomes 1. You have to go in a cyclic manner. So alpha 3 is equal to x1 y2 minus x2 y1, right? So I'll write just psi 1. So psi 1 will be 1 by 2a times alpha 1 plus beta 1 x plus gamma 1 y. So x and y we already found in terms of s. So I will substitute this just here. So this will be 1 by 2a. Alpha 1 is nothing but x2 y3 minus x3 y2 plus beta 1 is, okay, I'll write beta 1. So okay, can anybody tell what is beta 1, beta 2 and beta 3? Do you remember for the linear triangular element? So what is beta?
y2 minus y3.
Yeah.
y3 minus y1.
And this will be y1 minus y2, correct?
Minus y1.
So what about gamma?
Minus of x2 minus x3.
Yeah, so similarly this will be minus of x3 minus x1. This will be minus of x1 minus x2. Yeah. Okay. So I'm just substituting here beta. So y2 minus y3. What is x? X I have to substitute from here. It will be 1 minus s by a into y1. Sorry, not y1. It will be x1, right? Plus s by a x2. So this I have substituted. Then gamma 1 will be, so this plus will become minus. Same thing, I am going to substitute y as 1 minus s by a into y1 plus s by a times of y2. So why I am doing everything is I want to get psi 1 in terms of x comma y. I have to bring it in terms of s. So that is why I am doing all this. So 1 by 2a times, I will just expand this whole thing, x2 y3 minus x3 y2 plus I will simply write 1 minus s by a times of x1 y2 plus s by a times of x2 y2 minus 1 minus s by a times of x1 y3 minus s by a times of x2 y3. Again I have to expand these terms, minus 1 minus s by a x2 y1 minus s by a x2 y2 plus 1 minus s by a x3 y1 minus s by a x3 y2. I think only these two terms will cancel, x2 y2 so if I take 1 by 2a, so I have x2 y3 here, I have s minus a into x2 y3 here, so essentially this will become 1 minus s by a times of x2 y3. So I will circle the similar terms. this one. So this I have combined here. Let me take another color. X3 y2 I have at two places, this one and this one, right? Okay, I think this will also should be plus, because minus into minus will become plus, so that I have written here. So these two terms I will take my minus common, so this will be 1 minus s by a again. Another two terms, x1 y2, I have only one x1 y2. At the same time I have only x1 y2, x2 y1 I have one only, and similarly I have x1 y3 and x3 y1. Okay, so my 1 minus s by a is very common, so I take that outside, 1 minus s by a. So what I am left is with x2 y3 minus x3 y2 plus x3 y1 minus x1 y3 plus x1 y2 minus x2 y1. So if you recall, this was nothing but my alpha 1, this was nothing but alpha 2, this was nothing but alpha 3. So can anybody tell what this term is? Alpha 1 plus alpha 2 plus alpha 3, how much it will be?
2 into area.
Yeah, 2 into area. So essentially, if this will be equal to 2 into area, so my equation becomes 1 by 2a into 1 minus s by a into 2a. So these two cancel each other. Finally, my psi 1 will be equal to 1 minus s by a. Okay, so if you follow the same derivation for psi 2 also, it will be 1 by 2a into alpha 2 plus beta 2x plus gamma 2y. So alpha 2 is it will be 3, beta 2 will be y3 minus y1, x I as usual substitute, minus s by a into y1 plus s by a into y2. So we will expand this. x1 y3 plus s by a into x2 y3 minus 1 minus s by a into x1 y1. So it's not minus, oh yeah, it will be minus, and similarly minus s by a times x2 y1. This will be minus 1 minus s by a times of x3 y1 minus s by a x3 y2 plus 1 minus s by a into x1 y1 plus s by a into x1 y2. If you see the terms which are cancelling, these two will cancel. So x3 y1, I have two things. Similarly x1 y3, I have two things. So finally I'll get something like this 1 by 2a. So this will be 1 minus of 1 plus s by a. So it will be s by a x3 y1, and similarly this will be minus s by a x1 y3 plus s by a into x1 y2 minus s by a into x2 y1 plus s by a into x2 y3 minus s by a into x3 y2. So again, if I take s by a common, I will be left with x3 y2 plus x3 y1 minus x1 y3 plus x1 y2 minus x2 y1. This is again the same as the previous. This is small a. So again this 2a and this will also be 2a. So my psi 2 will be s by a. So again psi 3, if you calculate, it will be equal to 0. So you can simply substitute. You can just write psi 3 is equal to 1 by 2a times alpha 3 plus beta 3x plus gamma 3y. So it will be 0. Maybe okay, I'll again derive it, no problem. So again alpha 3 is nothing but x1 y2 minus x2 y1 plus beta 3 is equal to y1 minus y2 into 1 minus s by a into x1 plus s by a x2. This will be x1 minus x2 minus s by a into y1 plus s by a times of y2. This will be x1 y2 minus x2 y1 plus 1 minus s by a times of x1 y1 plus s by a times of x2 y1 minus 1 minus s by a of x1 y2 plus minus s by a of x2 y2. Then here it will be minus 1 minus s by a of x1 y1 plus minus s by a of x1 y2 plus 1 minus s by a times of x2 y1 plus s by a of x2 y2. So let us see which are cancelling each other. So first of all, I can say that these both will cancel, and similarly x1 y1 also this will cancel. I have here for x1 y2 I have one term here, I have one term here, I have one term here. So if I add, what I will get? So it will be 1 minus of 1 minus s by a minus s by a x1 y2, then x2 y1 I have minus here, I have plus here, and I have this one. So if I write plus, I can say 1 minus s by a, then plus s by a minus 1 into x2 y1. So if you see 1 minus 1 cancel out each other, plus minus into minus plus, plus into minus also cancel each other. So this will be 0. Similarly here also this will be 0. So 0 plus 0 I'll get as 0. Psi 3 is 0. Okay. So this is a long question. So what we intended was we have to calculate the psi I. Psi I we have calculated in the S and T coordinate system. So now we can develop the QI, right? So what is Q1 for this element? It will be integral over the boundary of the element Qn into psi 1 into ds. Okay. So in this case my Qn is nothing but it is given to be Q0, correct? So first of all, boundary means I can split the boundary into 3. So across 1 2, across 2 3, across 3 1. So these are my 3 edges. So I am integrating along the boundary. Along the 2 3 and 3 1 we say that there is no source term. So here the Q is 0. So this both will cancel out into 0. So I have only integration along 1 and 2. So what will be that integral? Integration along the edge 1 2, it will be Q0. My Qn is nothing but Q0. So which is given here. So if you see the question also, my Qn is nothing but Q0. So my Q0 into psi 1. Psi 1 we just calculated. The psi 1 was 1 minus S by A. Correct?
Sir, show me the question, sir.
Yes. So this is the question. So we have the single element. So we have node 1, node 2, node 3. So from the general xy coordinate we came to the st coordinate. So I calculated the shape function and the st coordinates, the interpolation functions. So I am just substituting them. So my Q0, so my psi 1 I just calculated 1 minus S by A. So what is this A? So A was, we decided it will be the base of this triangle, right? So in this case what is the base of the triangle? It is equal to H12. So I will simply write ds. So Q0 I can take outside. So this will be along the integral 1 to 2 means I am simply integrating from this point to this point. So if I integral along the st coordinate system, I am just integrating along the s from 0 to a, correct? So from 0 to a I am integrating 1 minus S by A into ds. So this will be Q0 times, so ds, integral ds from 0 to a minus 1 by a integral S ds from 0 to a. So this will be Q0 into, this will be nothing but a, and this will be 1 by a into a square by 2. So a minus a by 2 I will get Q0 into a by 2. So what is a? It will be H12. So my integral Q1 is nothing but Q0 into H12 by 2. So we calculated Q1. So we will now calculate Q2. Q2 is nothing but integral along the boundary Qn into psi 2. Okay. So similarly this integral also we will have the component only along 1 2, because along 2 3 and 3 1 the source terms are 0. So along 1 2 how will it be? My Q1 is nothing but a constant Q0. Psi 2 is nothing but S by A, right? So simply Q0 by A I can take. So this 1 2 is nothing but 0 to A SDS. So my Q0 by A into A square by 2, which is Q0 into A by 2. My A is nothing but Q0 into H12 by 2. This is Q2. My Q3 will be integral along the boundary Qn into psi 3 into ds. My psi 3 is 0. We just derived here, right? This value of psi 3 is 0. So I'll box the psi 1 and psi 2. Psi 2 is s2 s by a we just calculated. Psi 3 was 0. So this q term will be 0. So q3 will be 0. So if I write for this q for this matrix, it will be three element. It will be three terms because corresponding to each node, q1, q2, q3 of all the elements. So this was, if I make it q0 h12, I make it common. This will be 1 by 2, this will be 1 by 2, and this will be 0. So this is the boundary terms. So with this example, I hope you understood how to calculate the boundary. So boundary terms. So any doubt in this question till what we discussed? So
No, sir.
okay. So this was the one example we did. So similarly, the same example you can do. Instead of q0, you have to just simply substitute q0 into s1 by h12. So we can quickly do that. The functions are going to be the same. Only thing is my q is changing. So what is this? Qn is equal to q0 into s1 by h12. So this will be my s1 axis, this will be my t1 axis. So okay, so again the same psi will exist. Psi 1 is equal to, here s by s, instead of this will be a, so 0 comma 0, this will be a comma 0, this will be c comma b. Since this will be c, so this will be b and this will be a. We already derived what is psi 1 minus s by a, so here will be s1 by a, psi 2 will be s1 by a, psi 3 will be 0. So simply I have to calculate each q1. Q1 is equal to, again similarly here the integral will be only from 1 to 2 because the other two there is no boundary source. So from integral 1 to 2, which is this one, along the edge 1 to 2, qn into psi 1 into ds. So what is qn? Just substitute q1 into s1 by h12, right, into, so this entire thing is there, into psi 1. Psi 1 is 1 minus s1 by a into ds. The whole thing I have to integrate from 0 to a, because along this line my s1 varies from 0 to a. So q0 and h12 I can take it as outside. So what will be inside is s1 into 1 minus, I'll expand it actually. So it will be s1 minus s1 square by a ds. So this will be q0 into q0 by h12 integral 0 to a. This will be s1 ds will be s1 square by 2, it will be a square by 2 minus 1 by a into a cube by 3. So a square by 2 minus a square by 3, I will get it as a square by 6, q0 by h12 into a square by 6. My a is nothing but h12. So here I am, this edge's value is h12. So if I substitute that, q0 by h12 into h12 square by 6, so my q1 is q0 into h12 by 6. So if you compare with the previous term, we got q1 into q0 into h12 by 2 because it was constant. So here it is linearly varying from one side to another side. So because of that we got some variation like this. So similarly I can integrate q2. So q2 is nothing but integral, again here also it will be from 1 to 2, qn into psi 2 into ds. So what is qn? Qn is nothing but q0 into s1 by h12. My psi 2 was s1 by a. if you just go up, I've written psi 2 is S by A. See, in this case it is S1 by A, so ds. So ds is ds1. So here also I will substitute as ds1. Okay, so again my A is again already equal to h12 only. So q naught by h12 square. So this also 0 to h12, s1 square ds1. So this will be q naught by h12 square into h1 cube by 3. So this will be q naught into h12 by 3. q2 is q naught into h12 by 3. Okay, so q3 will again be 0 because the psi 3 is 0. So again we calculated the q terms. Q is equal to q1, q2, q3, which is equal to q naught h12 by 6. This will be 1, this will be 2, this will be 0. Correct? So any doubt for this? So this we will skip. So what we have to do in this, it will just be a combination of this and this. For edge 1 2 you have to use this coordinate system and do s1 do the integration, and for this edge you have to use the s3 coordinate system. So for this is coordinate is s1 t1. For this the coordination will be s2 and s3 like this, so you have to add both. So that we can skip for now. So for these two examples, is it okay? Is there any doubt? So how we calculated the boundary source?
No, sir.
Okay. So if you have any doubt, please you can intervene. Okay. So this is an objective question. So for a given 2D domain discretized into a finite number of 2D elements, the number of rows in the connectivity matrix corresponds to. So we have 4 options. First option, maximum number of nodes in any element. B is total number of elements in the domain. C is the minimum number of nodes in any element. D is the total number of nodes in the domain. So you are aware of what is a connectivity matrix, right? So what will be the number of rows? The number of rows in the connectivity matrix, what will it correspond to among these 4 options? So can you take a guess?
Number of elements.
Yes. So option B, right?
Yes, sir. Option B, total number of elements.
Yeah, okay. Yes, the answer is option B. So if we have a matrix like this, so number of rows will be this one, right? This will be row number 1, this will be row number 2. Okay, so this will correspond to element 1 and this will be element 2. So if you have more number of rows, they will correspond to the total number of elements. So what about column? What will they be?
That will be maximum number of nodes.
Yeah,
Any
okay.
element. First option.
Yes, first option. Okay. This will be column. Okay, fine. Okay, so we have a matrix, we have a domain which has been discretized into five elements. Okay, and there are totally we can say 1 2 3. So this is 1 2 3 4 5 6 7 8 9 10. So there are 10 nodes and there are 5 elements, correct? So can you guess what will be the dimension of this connectivity matrix for this domain? So we just saw, right? So what is the number of rows and what is the number of columns? So based on that, can you guess what is the dimension of the connectivity matrix for this domain?
That will be, sir, 5 into 4.
Yeah,
See.
5 into 4. So 5 is the now total number of elements, right? So we just counted it. So this is number 1, number 2, number 3, number 4 and number 5. So 5 elements, and this 4 corresponds to the maximum number of nodes in any element, right? So in this there are 4 nodes, in this there are 4 nodes, in this there are 3 nodes, in this element there are 4 nodes, and in this element also there are 4 nodes. So the maximum possible is 4. So answer should be 5 cross 4, correct? So yes, you are right, answer is 5 cross 4. So okay, so we have two cases. We'll try to derive the element connectivity matrix for the both the cases. So what they have given here is assume anti-clockwise sequence for local node numbering. So for example, if you take this, the local node number of 1 is given in each element. So if the 2, 3 and 4 should be in the anti-clockwise manner. So if I start 1 here, this should be my 2. This will be okay. I'll use another color. It should be my 2. So first of all, what will be the dimension of the connectivity matrix for the first domain?
4 plus 4.
Okay, so there are 4 elements and the maximum number is 4. Okay, so can you tell what will be the connectivity matrix? So let us start with the first row, which is element 1. So what will be the row number 1?
1, 1, 4, 5, 2.
Yes, it will be 1. So local number node 1 corresponds to global node 1, so it is 1. Similarly, local number 2 corresponds to global number 4. So let me write 1, 2, 3, 4. These are the local nodes, correct? So what is the number 3 corresponds to 5, number 4 corresponds to 2. Okay, for second element,
2, 1, 6, 3.
are you sure it is 1? Actually this 1 here, it is corresponds to the local node of the third element. So this is this thing, global. So answer will be
2, 5, 6, 3.
yeah, 2, 5, 6, 3. Okay, so what is for the element number 3?
5, 8, 6.
Okay, so this will be empty, right? Because there is no there are only 3 nodes in the third element. So what about 4?
7, 8, 5.
Okay. Okay, so now we will do for the second domain. So first of all, what will be the, so we saw the same question we saw in the last question. So the dimension is 5 by 4, sorry, 5 by 4. So 1 minute. Okay, so row number 1 for this. So let me do the node numbering first. Okay, can you tell for row number 1 now?
5, 2, 3, 3, 6.
Yes. What about second row?
4125.
Okay. What about the third row?
457.
Okay. This will be empty. What about the fourth?
7568.
Okay, 7568. What about the fifth one?
97810.
Okay. So I think with these two examples we have seen how to derive the element connectivity matrix for any domain which is discretized into any number of elements. Okay. Okay, so now we have the global stiffness matrix assembly. So this is my domain. So what I want is K55. So this is so let me do the local numbering. So 1 2 3 4 1 2 3 4 1 2 3 1 2 3. Okay. So what will be my K55? So this is my global node number 5. How from these options, what do you think will be the answer of K55? So first of all, from yeah, please go ahead.
Nothing else, sir.
Sorry.
Go on, sir. Nothing else.
Okay. Okay. First of all, for this K55, how many contribution will come? So what all the elements will contribute? So will the contribution be from element 1, element 2, element 3, element 4, all elements, or will it be only selected elements? So for the K55,
1, 2, 3, 4, sir.
all the yes. So there will be 4 terms, right? Totally. So can you say between B and D only there are 4 terms actually. So
D, sir.
yes. So how we are deriving it is, so first of all from the first element, it will be the contribution of the third node. So 5 5 is nothing but 3 3. Then from the second element again it will be 2 2. From the third element it will be 1 1. From the fourth element it will be this one, right? 3 3 again. So this will be the answer. So yes, you are correct. So similarly, let us solve for this. So here they are asking global stiffness matrix K57. So let me do the local numbering. 1 2 3 4 1 2 3 4 1 2 3 4. So this also I will make it as red for convenience. 2 3. Okay. So 5 7. So first of all, this is my global 5, this is my global 7. So which means this is the line which I am concerned. So first of all, for the global stiffness 5 7, so how many contribution will be there?
2.
Yes, because this line is common to both third element and fourth element. So from this itself we can guess that what will be the answer?
A.
Yes, A. So anyway, we will, for the sake of simplicity, for the sake of clarity, we will write once again what K1. So you will have contributions from the third and fourth element. So what will be the third element means? So since it is 5 7, so the corresponding local will be 2 1. Sorry, not sorry, this is for third element, right? 2 3 it will be. So third element it will be these two, and fourth element will be 2 and 1. So I hope there is no doubt in this question. So we shall move to the next one. So till now we saw about this is also how to get the global stiffness matrix element by element wise. So which for component wise we saw. So for now we will try to do for the whole. Okay. So first of all we will do the assembly first, and then we will calculate the values of the global stiffness matrix. So this is my element 1, and this is my element 2. So totally how many elements will be there in my global stiffness? What will be the size of the global stiffness matrix? Any idea?
2 cross 3, sir.
2 cross 3. Okay. So how did you get this?
2 element and each element have 3 nodes.
Okay. So total will be 2 cross 3 in the sense it will be a 2 rows and 3 columns, or is it like that?
Two elements, maximum number of nodes in an element.
No, this is not the connectivity. This is a stiffness matrix. So sorry for confusing. So this here coefficient is nothing but stiffness. Connectivity, yes, you are right. 2 elements into number of that will be 2 cross 3. So here I am asking like the stiffness matrix, like this K. So for element 1, what will be the number of elements? What is the size of the element stiffness?
3.
So it will be 3 cross 3, right?
Yes.
So for this will be also 3 cross 3, element 2. So what will be the global stiffness matrix? So while assembling, how will it be? So here we have 3 nodes. So based on that we have 3 cross 3. Similarly in this element also we have 3 nodes. So based on that it was 3 cross 3. But for the whole element we have how many nodes as a whole domain if you consider?
4 nodes, sir.
Yes, 4 nodes. So the size of the global stiffness matrix will be
4 plus 4.
Yeah, it will be 4 cross 4. Okay, so I'll go to the nodes. So since I don't have space there to write, I will write here. So this is my element. So this is my xy coordinate. So like this, there are 2 elements are there. So this is side A, this is side B. So local numbering it was this way, 1 2 3. Again for here it is 1 2 3, and when it comes to global it is 1 2 3 4. Okay, so we saw that global stiffness is, let us say it is K1. So this is the global stiffness matrix. So let me write for so okay, so we'll see element by element. What will be K11? So how many contributions it will have? Will it have 1 contribution or 2 contribution?
2 contributions, sir.
Okay, so what will be the this thing? So for it will be from the first element we will have 3 3, right? And from the second element we will have 2 2. Is this right?
Yes, sir.
Yeah. because here the contribution is from local number 2, here the contribution is from local number 3. So what about K12? So K12 is, if I have to highlight, it's this line. So how many contribution will K12 have?
1.
Okay, so what will be the corresponding this one from the first element?
K31.
Okay, K31. Okay. What about K13? So this is this line, right? So how many contributions it will have?
2, sir.
Yes. And what are the individual elements? So one from first element, one from second element. What will be the things?
3, 2, 2, 2, 3.
Yeah, it will be 3, 2 from the first element and 2, 3 from the second element. So K13 is done. K14. This is number 1 and number 4. How many contributions it will have? K14.
1,
And what will be the corresponding value?
2, 1.
Yes, K21 from the second element. Is it first or second? Yes, second element. Okay. So, okay. So K21. What will be the value?
0.
K21 is this one, right?
Yeah. Sorry.
Ah,
1, 3 at first element.
1, 3 at first element. Yes. So K22.
K11 at first element.
Yes. K23.
K12 at first element.
K24.
And is it 0, sir?
Yes, because there is no physical connection, right, between 2 and 4. What will be K31?
K23 at first element. K32 at second element.
Yes. Sorry. K32.
K21 at first element.
Okay. K33.
K22 at first element. K33 at second.
Yes. K34.
K31 at second element.
Okay, I'll write here. K41.
K12 at second element.
4 2
0.
4 3
K13 at second element.
This last will be
K11 at second element.
yes. Okay. So if we now make the large matrix, so it will be the 4 cross 4. We have evaluated all the terms. I mean, we have at least symbolically we have written all the terms. So this will be K331 plus K222 K311 sorry K321 plus K231. This will be K131 K111 K12 0 K23 K32 sorry 2 K211 K22 plus K33 this will be 2. It is fourth K31 of second element. Similarly, this is K12 of second. This will be 0 K13 of second element. Last will be K11 of second element. So this will be the global stiffness matrix. Right. So here we have evaluated the global stiffness matrix at the symbolically, but how to evaluate the each and every individual term? So we'll again draw the. We'll now see how to evaluate the each and every individual term. So this is my x and y. So the division was like this. One, two, three. Similarly, this will be 2, 3. So if I write the coordinates, this will be 0, 0. This will be a, 0. So this will be a, b, and this will be 0, b. Right. So this was my element 1. This was my element 2. So first of all, what is the so we have to eliminate the stiffness matrix, right? The equation is minus del square of u minus f is equal to 0. So what is del square? Write in black. So can anybody tell what is del square? Okay, so del square is nothing but dou square by dou x square plus dou square by dou y square, right? So if I say del square u, that means it is dou square u by dou x square plus dou square u by dou y square. So this is the meaning of del square. So which means my differential equation is minus of dou square u by dou x square plus dou square u by dou y square minus f is equal to 0. So this is my differential equation. So I will just simply compare it with the model equation. So I'll write it like this: dou by dou x of dou u by dou x plus dou by dou y of dou u by dou y. I can write it as this, like, so simply dou square u by dou x square, I am simply writing it as dou f by dou x of dou u by dou x, and this is minus f equal to 0. So I will write model equation. So model equation of minus dou by dou x of a11 dou u by dou x plus a12 dou u by dou y so here also I will take the minus inside. Okay, additionally there was, so from, can you compare these two equations and tell me what are the values of a11? Just simply compare both these equations. What will be the value of a11?
1.
Yes. So what about a12?
0.
Yes. So a21?
1.
Okay. a22?
0.
Okay. So okay, actually, so look these two terms carefully and then say once again. So here there is y and here also there is y. So here there is y, here there is x, and here there is y. So now you just compare and tell me. So what is a21, a22?
It will be 0.
Which will be 0? a21 or a22?
A21 will be 0 and
Yeah.
22 will be.
Yes. So you have to see carefully because dou by dou y is there. So inside you have to see what is the coefficient of dou u by dou y. So it is 1, and this corresponds to a22, and there is no dou u by dou x term, so which means a21 is 0. So this vanishes. This vanishes. What about a00?
0.
Yes. Okay. So in the last class we would have seen what is the Kij. So Kij for any element is equal to, so it is a11 Sij11 plus a12 Sij12 plus a21 Sij21 plus a22 Sij22 plus a00 Sij00. So this is the so do you remember this formula? So last class we would have discussed. So how this Sij comes, we did the weak form and we got the formula. So a12, a21, a00 you can cancel out. So finally my Kij for the eth element will be a11 Sij11. So in this case it will be simply, my a11 is also 1, so it will be Sij11 plus Sij22. So what is Sij11? So do you remember? It is integral over the element. So Sij, right? So it will be dou psi I by dou x into dou psi j by dou x into dx dy, right? So what is Sij for 2 2? So both will be y. It will be dou psi I by dou y into dou psi j by dou y into dx dy. Correct? Okay. So what is psi I for triangular element? Again we can recall 1 by 2a times of alpha I plus beta I x plus gamma I into y. Okay. So what is my dou psi I by dou x? It will simply be beta I by 2a. What is dou psi j by dou x, it will be beta j by 2a. What will be dou psi I by dou y, gamma I by 2a, dou psi j by dou x, sorry, dou y, gamma j by 2a. So this term you understand, right? So alphas are constant, so that will vanish while differentiating. So only if you partially differentiate with respect to x, only beta I will be there, and of course this 2 by 2a will be common. And similarly, if you want to partially differentiate with respect to y, this gamma I by 2a will be there, rest all will vanish. So like that I have derived this term. So first, so again Sij 1 so this will be integral over the element. So simply I substitute dou psi I to do, so it will be beta j by 4a square dx dy, correct? Sorry, not beta I, it will be beta j. Right? So we will see the first element arrangement. So for the first element, what is x1 y1? This is the first element, right? x2 y2 is a comma b, x3 comma y3 0 comma 0, x1, yes. So I'll write it again here. x1 is a, x2 is a, x3 is 0, y1 is 0, y2 is b, y3 is 0, double a 0, 0 b 0. Yes. Okay, what will be S11? It will be nothing but integral over this thing, beta 1 into beta 2 4a square dx dy. What is beta 1? Can anybody say? So we have seen in the previous examples also, right? What is beta 1? So we have a triangle like this, right? So this was our 1, this was our 2, this was our 3.
y2 minus y.
Yes, y2 minus y3. What is y2? B. Oh, sorry, this is not beta 2. This will be beta 1. Because S11, I and j both are 1, beta 1, it will be y2 minus y3. So y2 minus y3 is b. So it will be simply b square, right? Into dx dy. So if I take this b square by 4a square, what will be integral dx dy over the element? So integral dx dy over the element is nothing but area of the triangle. Is it correct?
Yes, sir.
Yeah. So this will be b square by 4a square into, so this will be a, right? So this will be b square by 4a. So what is area of the triangle? Half into base into height. So half into AB. So b square by 4a is nothing but 4 capital A. So b square by 4 into half of AB. So this is nothing but your S11 is b square by 2AB. Okay. Yeah. So like this you can keep calculating. So what is S12? Integral over the domain beta 1 beta 2 by 4a square dx dy. Okay, so due to some echo is coming, so yeah, thank you. So 1 by 4a square, beta 1 was y2 minus y3, which is b. What is beta 2? y3 minus y1, right? This will be 0. Okay, so this will be simply 0. What is S13? Integral over the element beta 1 beta 3 by 4a square dx dy. What is beta 3? Sorry, beta 1 is y2 minus y3, which is b. Beta 3 is y3 minus y1 is z. So what is beta 3? y1 minus y2, which is minus b. So this will be equal to b into minus b by 4a square dx dy. So minus b square by 4a square into area. So this will be minus b square by 2ab, right? Okay. Yeah. S21 will be same as S12 because it is symmetric. Since beta 1 and beta 2, you are just going to replace it by beta 2 into beta 1, which is nothing but the same. So it is going to be 0, correct? So what is S22? Beta 2 the whole square dx dy. So beta 2 is again 0, so this will be 0, correct? What is S23? This will also be 0, right? Because since beta 2 is 0. What is S31? Beta 3 beta 1. This is nothing but S13, right? Same as S13. What was S13? Minus b square by 2ab. What is S32? B2 is 0, right? So this will be 0. S33 beta 3 square. What is beta 3? y1 minus y2 minus b. So minus b the whole square is b square. B square by 4a square into dx dy area will be a. So this will simply be b square by 2ab. So we have calculated the terms of this Sij 11, I guess. So then we have this Sij 22. So the summation of these two matrices will be the stiffness matrix for the first element. So we will simply simply write Sij for the 11. So it was b square by 2ab.
Sir, we are doing global stiffness as well as element level stiffness.
So currently we are doing the element level stiffness.
Okay, sir.
So here we saw from the element level how to get the global level, right?
Right, yes, sir.
So once we get the element, we are going to add everything and make the global one.
Okay, sir.
Yeah. So I'll just And element level itself, there are two terms. So as I told here, so one term is related to S11 Sij11 and second term is related to Sij22. So we have till now calculated the elements related to Sij11, so which is nothing but this beta, related to the beta. So if you see here, b square by 2ab minus b, okay, probably I will write 1 by 2ab as common, b square 0 minus b square. What is the second row, everything is 0, third row is minus b square 0 b square. So this we have got. So Sij 22 we are going to solve. So Sij is simply going to be dou psi I by dou y into dou psi j by dou y into dx dy. So what is dou psi I by dou y? This will be gamma I into gamma j dx dy. Correct? Because if you differentiate this with respect to y, so this term will vanish. Similarly, x term will also vanish, and only the gamma I will remain. So this will be gamma I into, similarly this will be gamma j. So what is S11? Gamma 1 dx dy. What is gamma 1? Minus of x2 minus x3. Again, what are the values of x? A 0. So x2 minus x3 is minus x2 minus x3 is a. So here it will be minus a. So this will be minus a into minus a square into, sorry, gamma 1 by 4a square will also remain, because this 2a will get multiplied in 2 times. So 1 by 2a will be common for gamma I. Similarly for gamma j, there will be 1 by 2a, so they will be multiplied to get 4a square. So a square by 4 capital A square into dx dy. So this will be a square by 4 capital A square into dx dy. This will be a. So this will be a square by 2ab. So what is S12? Gamma 1 gamma 2 dx dy. Gamma 1 is minus a. What is gamma 2? Gamma 2 is minus of x3 minus x1, right? So that will be minus of 0 minus a, minus of minus a, which will be, sorry, this will be into plus a. So this will be minus a square by 2ab. What is S13? Gamma 1 gamma 3 dx dy. Gamma 3 is, gamma 1 is minus a, gamma 3, what is gamma 3? Minus of x1 minus x2, a minus a, which is 0. This is 0. S21 is nothing but S12, which is minus a square by 2ab. S22 is gamma 2 square by 4a square into dx dy. What is gamma 2? Gamma 2 is simply a square. You can say this is a square by 2ab. S23 will be 0 because it will involve term gamma 3. So gamma 3 is 0. And one more thing, S31, S32, S33 all will be 0. Why? Because gamma 3 is 0 always. So if I want to summarize this Sij 22, what will be? It will be 1 by 2 AB. So it will be a square minus a square 0 this will be minus a square 0 will be 0 0 0. So this was my second, this is my first. So I am going to simply add both. So Kij for the first element will be 1 by 2 AB. The first will be a square plus b square. The second will be minus a square. Third will be minus b square. I am simply adding both. So here minus a square is there, here 0. And similarly this will be minus b square 0 b square. Correct? So this is
Yes,
the
sir.
element stiffness matrix for element 1. Okay. So element 2, if you observe, it will be it is like the same configuration, right? So this is number 1, this is number 2, this is number 3. So this is also side is equal to A, this is side is equal to B. So similarly, if you see here, so 1 2 was along B, 2 3 is along the diagonal, and 3A is along the 3 1 is along A. So similarly here 1 2 is along B, 2 3 is along the diagonal, and 3 1 is along A. So the for element 2 also the Kij will be the same. Minus a square okay. So actually it's a property of the triangle. So since the node numbering is of the same this thing, just that if you rotate this element 180 degree you will get element 2, because the 3 1 is exactly along the line A, 1 2 is also along the line B, and 2 3 is along the diagonal. So when you the element wise the stiffness matrix will be the same. So global stiffness matrix we need to see, right? So global stiffness matrix, so K331 plus K22 of second. So what is K33 plus K22? So this will be K33 of the first, this will be K22 of the second, right? So the global stiffness matrix, it will be simply 1 by 2 AB, this will be a square plus b square, correct? And what was K12? It will be K31 of the first element. So K31 of the first element is minus b square. Again, what is this? K32 of the first element and K23 of the second element. K32 of the first element, K23 of the second element is going to be 0. What is K14? is K21 of the second element minus A square. So what is K21? K13 of the first element, which is minus B square. What is K22? K11 of the first element, A square plus B square. What is K23? K12 of the first element, minus A square. What is K24? It is 0. So like this, one by one you have to assemble. So what is the K31 of the global matrix? K23 of the first and K32 of the second. K23 of the first, K32 of the second. Correct? Is this right? 0. K21 of the first element, this one minus A square. What about K33? K22 of the first element and K33 of the second element, A square plus B square. What is K34? K31 of the second element. What is K31 of the second element? Minus B square. Okay, what is K41?
K12.
Yeah, K12 of the second element. Okay, what is that?
0.
K12 of the second element. This one, right? This first element, this second element. What is K42?
0.
Yeah, 0. This is K13 of second element, minus B square. What is the last one?
K11.
K11 of second element, which is this A square plus B square. So this is the total. So if you see the question, I can assume A, B is equal to 1. So if I substitute that, so this will be half into this will be 1 square plus 1 square, 2 minus 1 0 minus 1 minus 1 2 minus 1 0 0 minus 1 2 minus 1 minus 1 0 minus 1 2. Okay, so finally we got the global stiffness matrix. Okay, so this is the procedure. Okay, so any doubt in this? So how we got this? So we did the individual element stiffness matrices, right? And in this question it so happened that the numbering was just in the same sequence, just that the element is in a different rotation. So we can use the same element stiffness matrix. If the numbering was different, then for example, if say this was 1, this was 2 and this was 3, then you might have need to evaluate the element stiffness matrix of the two, just like we did for the one, so step by step. So that eliminated the process for us. So because of which we are simply able to get the second element stiffness matrix, and finally we added both. So this is the global stiffness matrix. Any doubt in how we computed it?
No, sir.
Okay. So this is one question. So the derivative of the primary variable along a plane of symmetry is 0 in which direction? So parallel to the plane, normal to the plane, inclined to the plane, cannot say. What is the, can you guess what could be the answer? So the derivative of the primary variable along a plane of symmetry. Okay, so let me try to draw. Suppose, let us say that you have a domain like this, and first of all, for the case of symmetry, we need all four conditions to be symmetric. So first condition. So can you say what are the four conditions for symmetry of the problem? What are the four parameters which need to be symmetric?
Geometry,
Yes.
boundary conditions,
Yes.
Metal properties and force.
Yes. And force. So assuming that all four are there, so let us say that these two are symmetric. So we can say, we can assume this. So this, if this was my x and this was my y, so in this symmetric this thing, in this plane, what will be the condition for u? So derivative. So this will be x, this will be y. So what will be the derivative condition here in this plane?
0, sir.
Yeah, so along which direction? But
x,
okay, so
y
here,
by 2x,
so here,
y,
yes. So which means in this plane, so is it the parallel or a normal or inclined?
normal.
Yes, normal. So answer is B. So always when you are looking at a plane of symmetry, the derivative is along the normal direction. So for this, this plane is along y axis means, so dou u by dou x is 0, and similarly for this, it is this case. Correct? It was along the normal. Okay. So I think we may have time or no, I'm not sure. So but we have one more question, so we'll try to solve this. So we'll just simply try to solve this thing. So is there any symmetry in this question, do you think? Based on the geometry, based on the boundary conditions, based on the
differential equation.
yes, okay, yes. So differential equation is symmetric, right?
Yes, sir.
Yes. So can you find a plane of symmetry here? Okay, we'll try to do one by one. So here u of x of 0 is x square. So along this, what will be the value of u here? So this is x equal to, so this is x means this is my 0 comma 0, this is my 1 comma 0, this is my 1 comma 1, this is 0 comma 1. What is
It is symmetric along the line y equal to x.
Yes, correct. So this will be symmetric, right? Because here my u is 0 and here my u will be, sorry, one minus 0. So here u will be 1. Similarly here also u will be 1 and here u is 0. So along this direction there is a symmetry. Okay. So we can try to divide the like this. So we can try to segregate the domain in this manner. So this is my global. So local, if I write 1 2 3 1 2 3 4 1 2 3, so like this we can write, right? Okay, first of all, what will be the size of the global stiffness matrix for this discretization which I have done here?
4x3, sir.
Okay.
6x6, sir.
Huh? 6 cross 6, right?
6.
Yes, because if you see here, there are 3 nodes which are additionally which have come into play. So if I reconsider, I can do the numbering like this. Because we are no more we are dealing with this, we are simply dealing here, right? So in this only u3 is a unknown variable, the rest u are known because of the boundary condition. So here what is u6?
0.
Yes. What about u5? So here along this line it is 1 minus x. So in this point this will be u5, right? What will be x u value there?
One minus x only.
Yes, 1 minus x.
0.5, sir.
Yeah, I was yes, correct. 0.5.
0.5.
Yeah. So what will be u4?
U4 is 0, sir.
Is it 0 or
U4 is 1. U4 is 1.
yeah? What about u1?
U1 is 0.
Yeah. What about u2?
U2 is
This one.
0.5.
Yeah.
Whole square is 0.25, sir.
0.25, right?
Yes, sir.
Yeah. So we have u1, u2, u4, u5, u6. Only u3 is unknown. Correct? So
Yes,
if we look at the previous examples, try to assemble the global stiffness matrix. You can get the, if you calculate the boundary terms, you will be able to get what is u3, right?
sir.
Yes. So which means you have to simply consider this third row into this thing. So it will be, yeah. Okay. So I think since it is time, we will stop here. So maybe we will try to just compute the stiffness matrices. Correct? A stiffness matrix we have already done here for this case. For this case we have done the triangular case. So similarly we can calculate for this triangle also. So we can calculate. So this will be element number 1, this will be element number 2, this will be element number 3. For element number 2 and 3, the stiffness matrix at the element level is going to be the same. For the element 1, the stiffness matrix will be different. It will be the rectangle. Okay, so we will try to write just interpolation functions, right? So let us say that you are working upon the rectangle. One, two, three, 4. So if you choose the local coordinate system like this, so do you remember what is psi 1, psi 2, psi 3 and psi 4 for the rectangle for this case? So let us say this is side A, this is the side B.
1 minus x bar by a into
Ah.
1 minus y bar by b.
Yes. What about this x2? It will be x bar by a into 1 minus y bar by b, right? X3 will be x bar by a into y bar by b. X4 will be y bar by b into 1 minus x bar by a, correct? Okay. So this way we have got this thing. Again, for this equation, so assume k equal to 1. So if you assume k equal to 1, so it will be same as last equation, right? The del square is equal to 0. So minus del square u will be the case here also. So for that thing, our kij will be you can say it will be Sij 11 plus Sij of 22. So what is Sij 11 will be integral dou psi I by dou x into dou psi j dou x into dx dy. So Sij 22 will be dou psi I by dou y into dou psi j by dou y. So here we can say in this coordinate system dx bar dy bar, right? So I'll just try to evaluate one term. So what is dou psi I by dou x? So if you differentiate it, you will get it as if I expand psi 1, it will be 1 minus y bar by b minus x bar by a plus x bar